Hey, I'm Stefan and I'm the head of product quantum platform at IQM Quantum Computers. In today's video, I wanted to show you how you can get started easily with IQM Resonance and Qrisp. In order to do this, I headed over to IQM Academy to give me a Get Started notebook. Under this section, we've put a additional module that says Get Started with Qrisp on IQM. I open this one and download the corresponding notebook. I've now opened it in my favorite editor, and this notebook already contains all the bits and pieces I need. To start with a fresh environment, I'll clear all outputs. To get started, I need a Python environment I can run my code in. In order to do that, I'll create a new environment. I'm going to go ahead and choose a Python environment. I'll go for a new one. I'll use virtualenv in this case, and I'll choose Python 3.11. Cool. In this notebook, we will see how to get started with Qrisp, how to run a Qrisp program on an IQM backend, and how to use Qrisp libraries to implement some quantum algorithms in a very easy fashion. I still need to install the Qrisp package. I can do that with this first cell. The %% capture will suppress the output of this cell. In case you experience any problems, you can delete that line in order to see the debugging or logging information. The command to install Qrisp is pip install Qrisp and in rectangular brackets IQM. This allows you to use Qrisp in conjunction with IQM hardware. For some systems, you'll need to put those in quotation mark. For example, as I'm using a Mac here, I will need to add these quotation marks before I execute the cell. After installing the package, you can get started writing your first Qrisp program on IQM hardware by importing the Qrisp package. A core aspect of Qrisp is the use of quantum variables such as quantum float, as in this example. So it allows us, for example, to do calculation with these quantum float objects. To start with, we'll just run it on a simulator first. So we define a quantum float. We define it to be 2. Then we add it together with another 2. And then we do we retrieve the measurements of this calculation. And as we expected, the outcome is 4 with a probability of 100%. This was the simulator. Now we want to run this on real quantum hardware using IQM Resonance. In order to be able to execute the next cell that is really using an IQM backend, we need an API token. And you can create your own API token on IQM Resonance by registering for free. So I'll head over to my browser, and instead of IQM Academy, I'll go to IQM Resonance, another service of IQM's quantum platform. And on IQM Resonance, I can log in with my account if I already have one, or I can sign up for a new account here. So I'll go ahead and sign up for a new account. So I input my email address, enter the information for export control, set some password, accept the terms of use. Of course, I'll read them beforehand. And the privacy policy. And after I've checked those, I continue with the verification. So I'll now need to check my email and confirm with the verification code I just received. Cool. After that, I'm logged into IQM Resonance. In order to now work with IQM Resonance, and make use of the free credits in my account, I need to create an API token. So I click here to create my API token. It will expand the draw on the side, and I can generate an API token here. So I copy it, head over again to my notebook, and make use of my token within my notebook. So after I've inputted my token, I can connect with an IQM device. In this case, I'm choosing the 54-qubit device IQM Emerald, and I'm executing the very same circuit I've been running before in the simulator. So if I hit execute, the very same program will now be sent to a quantum computing backend, so to an actual quantum computer. We can actually see the job I just submitted on the IQM Resonance dashboard. So it's here under my latest jobs. So I can see this code ran 4 seconds on the IQM backend. I can see T1, T2 times, gate errors, and other metrics about the calibration status of the quantum computer at the time of execution. And I can also see that the most common result is 4 with a probability of around 55%. The other result are a result of the noise that is present on actual quantum computing hardware. Of course, I could increase the number of shots, but I could also go to more advanced examples. And in this case, I'm using the VQE module that is present in Qrisp in order to perform a chemistry simulation on a quantum computer. At its core, VQE works by defining a problem Hamiltonian that encodes the physics of some system of interest. And we want to create a parametrized quantum state, the ansatz, that allows us to be evaluated on a quantum computer so we can retrieve the expectation value. With a classical compute part, a classical optimizer, we iteratively update the parameters that are used within this ansatz to approximate the ground state energy of our problem Hamiltonian. In this cell, we try to load the PySCF package to define the problem Hamiltonian for the hydrogen molecule. As PySCF is only available to Linux and Mac users, there is an alternative here where we directly define the Hamiltonian. Then we define the ansatz for the quantum circuit, so the parametrized quantum circuit used to explore the quantum states and approximate the solution. And then we use the VQ problem class to find the solution that corresponds to the ground state energy. Depending on the device used and the credits available, this might not be possible within the starter tier. While my code is running, I can check the progress of my individual jobs on the IQM Resonance website, and I'll see live updates of the job being or the multiple jobs that comprise my VQE algorithm from moving to in the queue to being run to being completed. After executing the algorithm on the hardware, we not only see the result, but we can also look at the plot. We can see how the energy with additional iterations of our VQE algorithm approached the minimum we got as a result. Another experiment we can try is Grover's algorithm. It's a very well-known quantum algorithm that provides a quadratic speedup for searching in unstructured data. The advantage of Grover's algorithm is really for education because I think it illustrates some principles of quantum algorithms pretty nicely. You can learn more about Grover's algorithm on IQM Academy. Qrisp has a module for Grover's algorithm. In order to use it, we define an oracle. This is a function that marks or tags the state we're looking for. Normally, this will be related to the search problem we're addressing. In this case, we just arbitrarily tag the state 2. In order to now perform a Grover algorithm search, we define a quantum float that we perform Grover's algorithm on. In this case, we use 3 qubits for that. And then we provide both the quantum float variable, the oracle, and the information about how much winning states there are. And we execute this both on the simulator and on the actual quantum computer. And we see that in both cases, we retrieve the result 2, which is the state we've tagged before. On the quantum computer, this is accompanied by some noise, but the most dominant result is still the 2. With IQM Resonance free account, you can get started with quantum computing today. And I'm really excited to see what you will be experimenting with and how you will innovate in quantum computing. Thanks for tuning in.